Hello everyone and welcome to this lecture. Today we're going to introduce MapReduce, which is a very important paradigm of high performance computing and data analysis. MapReduce has been presented for the first time in the paper from Google entitled MapReduce, Simplified Data Processing on Large Clusters. In that paper, authors defined the MapReduce as a programming model and a corresponding implementation in the backend for processing and generating large dataset. But to really understand the reasons why MapReduce has been designed, we have to go back in time. It is 2004. It is the beginning of the multi-core era, and there is an industry-wide shift towards multi-core machines. The scenario of reference is the Google Cloud infrastructure environment, in which a large amount of raw data had to be processed, for instance, scrolling web documents or processing very large logs of web requests. From this processing, additional derived data were computed, for instance the inverted index, which is quite crucial for information retrieval systems. Existing solutions were usually complex, and the issues were related to a large input data size, the necessity to handle the parallelization of the code, and the distribution of the data among the workers, not to mention implementing robust code to handle the failures. These are indeed key challenges in the throughput computation in general. And so, the idea on which MapReduce builds on is moving the complexity into a unique and unified backend, which should be able to automatically parallelize the code and distribute the data among multiple machines. This is to simplify the user's defined solution as much as possible, considering a simpler solution with more input data. The idea is to decompose the computational problem into multiple smaller tasks in a divide-and-conquer fashion. The simplicity in the user-defined code is however paid off by imposing to the user code to comply with the computational paradigm imposed by the framework. This is indeed an anticipation of a popular software engineering principle that will be later named as the convention of a configuration principle. The computational paradigm of MapReduce is set on two core functional primitives, from which it also takes the name, the map and the reduce functions. On one hand, the map applies a function f to all the items of the input list, whereas the reduce function applies a function of two arguments cumulatively to the items of the input list. These two primitives have been readapted into the MapReduce framework in order to express with the idea that the entire computation can be reformulated in terms of these two operators on the set of key value pairs. So in more details, the programming model of MapReduce is first of all expressing the computation in key value pairs, input and output. The user has to define two functions, the map function, which takes an input, a key value, and produces a set of intermediate pairs, and the reduce function, which combines all the intermediate values mapped to a specific key and produces a set of merge output values, usually 1. Another convention imposed by the framework is that intermediate key value data type are strings by default, so in case different types are required, this is a matter of user code to do this conversion. The classical and most famous example of MapReduce, also reported in the paper, is the WordCount problem. We want to process a collection of documents counting the number of occurrences of words appearing in these documents. The computation is then expressed by a single map function which takes an input, a document, and emits an intermediate pair for each word and a 1 as an occurrence. All the occurrences of the same word, in this particular case, are grouped and pass as input to the reduce function, which performs the actual accumulation of the counting. This is very simple. There is another example, a bit more complex and potentially more interesting, which is the reverse web link graph. The map function output target and source pairs for each link to a target URL found in a source page. The reduce function concatenates the list of all the URL associated with the given target URL and emits the pair. The reverse web link graph is fundamental for the Google PageRank algorithm, which was actually the algorithm adopted by Google to generate the ranking of results in a search engine page. The more a page has other pages linking to it, the higher the position in the ranking, assuming then that that page was a central reference in web search. In this particular example, it is worthwhile noting that all the operation in combining the links pointing to a target page is indeed performed by the entire MapReduce framework. So the reduce function in this case is very simple, is indeed the identity function. Now let's have a closer look at the whole execution workflow, so going much more into the details of it. We start by the map invocation. So the map invocations are actually distributed across multiple machines by automatically partitioning the input data into a set of m different splits. And this operation is performed by a component of the MapReduce backend, which is called the reader. The input splits can be then processed in parallel by multiple machines. On the other hand, reduce invocation are actually distributed by partitioning the intermediate key space into r different splits by means of a partitioning function, which is by default the hashing of the intermediate key module r. This leads to the conclusion that with the full configurations, intermediate keys must be hashable. In fact, strings are. The user program then forks into many copies on a cluster of commodity machines. One of this copy is a special one. This is the master copy. This copy of the program will be in charge of monitoring and coordinating the other workers' copy. In fact, the master will keep a map with the status of each worker and will assign to each worker one of the mmapper task or one of the reducer task. It is important to emphasize that the number of tasks is not the number of workers. It's very different indeed. And in fact, the number of tasks should be much larger than the number of workers, so that multiple workers can perform map or reduce tasks, improving dynamic load balancing and allocation. In classic configuration, reducer are usually a small multiple of the number of workers. For example, 2,000 workers lead to 5,000 reducers with 200,000 mappers. So there are m mappers and r reducer. The master copy picks on either workers and assign a task, either a map or a reduce task. A mapper reads the input from the corresponding splits and produce the intermediate key value pairs, which are initially buffered into the main memory. Periodically, this buffered pairs are written to local disk, and these locations communicated to the master to be notified by reduced workers. When a reduced worker is notified by the master, it uses remote procedure calls, so RPC calls, to read from this local disk. And at this point, another component of the MapReduce comes into play. It's the combiner, which collects the intermediate key value pairs, group the pairs by key, and sort the values in order to pass the groups to the corresponding reduce workers. And finally, the reducers write their results into r different output files. Once the execution is completed, there will be r different outputs produced. And these files can be indeed combined or not, and usually they're not, because they are also potentially the input for another MapReduce job. So this is the overall workflow execution. However, there are some other bits that we left out in the discussion. One, and quite important one, is the fault tolerance. The MapReduce framework is designed to handle the failures via re-execution. Worker failures can be detected by the master by sending periodic heartbeats. In progress and completed map tasks are re-executed because their output is stored on the local disk of the machine where the fault was detected. As for the reducer, only in progress tasks will be re-executed. In case of a master of a failure, although unlikely, the fault can be handled via re-execution from checkpoints periodically collected. Additional refinements of the framework include the use of locality, especially for the mappers, which read the input at local disk speed, and so otherwise using rack switches, on the other hand, would definitely cap significantly the read rate. In case of a segmentation fault is detected due to a bad record in the disk, a UDP packet is sent to the master with a sequential number of the record. If the master sees two failures coming from the same sector, that sector will be automatically skipped and so ignored. As for the reducer, additional customization to the workflow can be provided by compressing intermediate data wherever possible to speed up the acquisition, and defining custom combiners acting as a grouper and a filter in the data to be passed to the reducer. So the MapReduce framework represents a very elegant and smart solution which had a huge impact on HPC paradigm and infrastructure. Indeed, the MapReduce had a tremendous effect on many research fields, for example data mining and machine learning. Looking for papers mentioning MapReduce on Google Scholar, you will find more than 120,000 hits, some of them very recent. And so in the next lecture we go to the details of MapReduce for machine learning on multicore, a work that was presented by Andrew Eng at the NeurIPS conference 2006, which has been influential in introducing the HPC practice into the machine learning community. Moreover, we will also analyze existing implementation of the MapReduce algorithm as part of the aggregation framework included in MongoDB. Thank you very much for your attention.